Any questions about anything from last time? Somebody asked at the end of last hour, where is this all headed? And I would say it's headed right here. Because today I'm going to sort of harvest some of the things that we can get out of the Cauchy integral formula. And two wonderful things that pop out right away are Liouville's theorem and the fundamental theorem of algebra. So that's the plan for today. This is a biggie. Kind of a highlight of the course that we can do that. But before I dive into that, last time I needed this fact that you can differentiate under the integral sign of a simple thing like I have there. I needed that in proving the Cauchy integral formula on a disk. And I didn't do it last time because it was a homework problem. I wanted you to experience working on that. The fact is you can differentiate, that function inside the square brackets there is an analytic function of w. And you can show that you can differentiate under the integral sign and get the what you expect when you do that. Okay, so a proof would be, I'll call that square thing in the square brackets h of w. So it's a function of w. Notice that it's a function of just w, not z, because z is the dummy variable. But when I differentiate inside, I use partial derivative notation there for the complex derivative with respect to w. Anyway, when I start working on the difference quotient, I get h of w minus h of w naught. And I write that out by definition. And then just to cross multiply and do a little bit of algebra, that thing inside the integral, the numerator is w minus w naught, which, from the point of view of that integral, is a complex constant over z minus w times z minus w naught. And so I can pull that complex constant out front of the integral. And I get this integral. And when you look at that integral, you say, aha, I can see that as w, well, let's say I need to divide that difference quotient by w minus w naught. So that would make this w minus w naught cancel out. And so the difference quotient, you expect, as w tends to w naught, that's going to be a 1 over z minus w naught squared. Okay, that's what we expect it to be. So what I need to estimate to show that the difference quotient does do what I expected it to do, I'll call that integral with respect to 1 over z minus w naught squared. I'll call that I naught for integral sub naught. Okay, the difference quotient minus I naught then, if you write it down, that difference quotient was the z minus w times z minus w naught in the denominator, and the limit's going to be a z minus w naught squared in the denominator. And you do that same kind of algebra of cross multiplying, and you get that that's another w minus w naught in the numerator times something. And I can pull that out. And that's going to be the key to showing that this goes to 0. I'll have a w minus w naught in the outside there in front. And so all I have to do is get a bound on that integral there. And that was the key to the problem. Once you do the algebra, you have to figure out I need to get a bound on that somehow. Because then as w goes to w naught, I'd get 0 in the limit. And that would mean the difference quotient tends to that I naught. Okay, so the best way to deal with that kind of thing is to draw a picture. This gamma was just a curved segment. It works the same if it's a closed curve. And of course, you're going to calculate this. You don't want w or w naught to be on gamma, because then that integral wouldn't make sense. So w naught is not on gamma. And so to bound that, I just need to show that as z of t goes along that curve, that the distance from that point to w naught is at least bigger than something. I need a greater than or equal to inequality for the denominator. Okay. Well, let's call the distance of w naught to the curve d, little d. That distance of w naught to the trace of gamma is the minimum of z of t minus w modulus as a ranges over the range of the t ranges over the parameter range. Okay, that's a continuous function. non-vanishing on the curve, and so it has an absolute minimum that's positive. So it's kind of important to note that that distance is positive. Okay, and now W is going to slide into W naught, and we just have to keep it away from the curve. So I drew a disk that would work there. I take a disk of radius r, and that just has to be smaller. The radius has to be smaller than the d over d. And then it would guarantee that W stays away from the curve. So it'd be natural to take r equal d over 2. That would certainly do it. Then when you estimate that, you'd have denominator estimates. Those are greater than or equal to. So when I do the basic estimate, I get that that's less than or equal to 1 over d over 2. That's the distance from W is bigger than or equal to that, times the distance squared from W naught, times the length of gamma. So, and that's the bound I need. Okay, that's how you do that kind of problem. I wanted you to wrestle with that just to experience thinking about that kind of stuff. By the way, if there was a function phi on the curve, it would just be something in the numerator there, and it would be bounded, and I just have another m there to bound. So that wouldn't change the calculations at all. Questions about that? An interesting fact, you can do the same thing if it's exactly the same reasoning. The algebra gets a little hairier, but exactly the same reason shows you can integrate, you can differentiate under the integral sign for higher powers in the denominator. And it's the same work, just a little bit more algebra. Which leads to that observation that you can get higher order Cauchy integrals formulas on the disk. So let's see, in this picture, I've got a function that's analytic on a bigger disk, and I'm going to take this smaller disk of radius little r inside, and that curve is a circle of radius little r about z naught, and A is a point inside that circle. Well, the Cauchy integral formula I proved last time is the first one there, and when I apply that fact about differentiating under the integral sign, I get a higher order Cauchy integral formula, and as the remark, I can do that again and again and see that f is infinitely complex differentiable, and the formula there, if I do it n times, I get an n factorial in front. Okay, and now I'm going to get the big theorems today by looking at that last formula and estimating it like this. So here I'm going to let A equal the center point. Then if you think about that, the z is going around here. Z minus z naught is always r. And so if I estimate this using the basic estimate, and let's say that f is less than or equal to m on the curve, trace of the curve, then when I do the basic estimate, I get the famous thing called the Cauchy estimate. The nth derivative of f at the center is less than or equal to, let's see, what am I going to get? N factorial over 2 pi m over, let's z minus the center, z naught, would constantly be equal to r, times the length of the curve, which is 2 pi r. So that's the famous thing called the Cauchy estimate. Cauchy estimates. If you have that picture above there, then you get that the nth derivative of f at the center of that circle, it needs to be analytic on a slightly bigger circle for this to hold. Let's see, the 2 pi's there cancel, and 1 power of the r cancels. So it's less than or equal to n factorial m over r to the n. Famous estimate, Cauchy estimates. Questions about that? Well, the case equal n equal 1 is kind of fascinating to think about. Because it's going to spit out Liouville's theorem. The derivative of f at the center can't be too big. If this were just a differentiable function, real differentiable, like in R2, I could push it around and deform it make it have a gigantic derivative at the center, and it'd still be nice and smooth, even and nice and bounded on the boundary. But if it's analytic, then it can't do no such thing. This is less than or equal to m over r to the 1, where m is equal to the max of mod f on the trace of C. Okay, and that leads immediately to the famous theorem by Liouville. A bounded entire function must be constant. I'll say with these. Constant. So bounded means f is less than or equal to something on C. And entire means f is analytic on C, on the whole complex plane. And the proof is going to be a snap from that Cauchy estimate. Pick a z naught in the complex plane, any old place. Then the Cauchy estimate with n equal 1 would yield that f of z naught is less than or equal to the max, that m is the max on C now, divided by a radius of a circle. But there's no limit to how big we can take that radius of that circle. So the aha moment is that.
Should that be the derivative of that?
Yes. Thank you. God, I do that all the time, don't I? Usually in the reverse order. So let's see that. And so, we can let the r go to infinity. Increase out and become arbitrarily large. And we conclude that f prime is 0. And that was an arbitrary choice. So z naught arbitrary so we conclude that f prime is identically equal to 0, and that implies f is constant. So that's all there is to it. So what a simple proof. And that is going to be the basis of our fundamental theorem of algebra. By the way, Liouville's theorem is way false, r to r. It's very easy to think of differentiable functions that are bounded. So, for example, sine of x is bound. It's differentiable. In fact, it's given by a power series that converges on the whole real line. Definitely not constant. And if you think about that now, say, well, this is something to think about. This complex version of the sine function is e to the iz minus e to the minus iz over 2I, or if you prefer, the famous power series. That would agree with the real one on the real line, but because of Liouville's theorem, that means that that complex sine function can't possibly be bounded on the complex plane. because it's not constant. It's not constant on the real line. So it's an unbounded function. So way different in the complex case than the real case. Something to note. Okay, but so I'm eager to get to the fundamental theorem of algebra, so I won't think more about that now. Questions about anything? I'm going to give this next thing a name because I'm going to use it when we do residue integrals and various other moments in the rest of the class. I call this the basic polynomial estimate. It's pretty useful in a lot of situations. So I'll have a polynomial, a complex polynomial, p of z equals an z to the n plus etc. down to a1z plus a naught. That's a complex polynomial of degree n bigger than or equal to 1. The constant case doesn't make, we're not thinking about that. And so for it to be degree n, the degree of equals n means that the an term is not 0. Then the basic polynomial estimate is there exists a radius r bigger than 0 and constants and real constants zero less than a less than b, such that we get the basic estimate that a mod z to the n, degree n bigger than or equal to 1, a z to the n is less than or equal to the modulus of p of z is less than or equal to b times modulus of z to the n. That means that the polynomials on the complex plane grow at infinity for big Z, like Z to the n. There's constants that squeeze it in bigger than 1 and less than 1 on the other side. Okay, so their behavior for when modulus Z is big is squeezed in between those things. So it acts just like Z to the n, and that's a way to think about that. In growth. So that's the growth of a polynomial.
How does the radius r greater than 0?
Yeah, that was what I was going to write next. When mod z is bigger than r. It could have finitely many zeros, and that would mess up the left-hand side. So I need to say when mod z is bigger than r. So it's for big Z. And a remark is that those A's and B's can be really close together. Let's see. We're going to have A is going to turn out to be less than the mod AN is less than B, and they can be as close to mod AN as you want. You just need a bigger R, perhaps. It can be as close to mod AN as desired. You might need a bigger R to do that. And that'll fall out when I do the proof. The proof is just going to be a picture, basically. Let's see, if I divide that polynomial by z to the n, that would isolate the first coefficient, an, and then I'll have a bunch of stuff that has z's in the denominator. Let's see, there'd be an an minus 1 over z to the 1 plus etc. We'd have an a1 over z to the n minus 1 plus an a naught over z to the n plus. And those z's in the denominator mean that that tends to 0 as z goes to infinity. So let's call this thing right here h of z. An important thing to note is that h of z goes to 0 as mod z goes to infinity. Okay, so I'm going to draw a picture now. an is not 0, so here's 0. Here's an. See if I can do this. I'm going to draw. I'll draw a dotted line circle. Doesn't look like a circle. Darn. Okay, here's an an. Okay, here's a smaller circle and a bigger circle. Okay, an is not 0. And so I'm thinking I need to put, let's see, I should probably draw my circle here. Blast. Try again. Oh, that's not too bad. This is my h of z. This is my h of z, my plus h of z. So that's an plus h of z. This point right here. This is an plus h of z. H of z is really small. So this is like a little circle of radius epsilon. An's not 0. And so that's my epsilon. The b is going to be this radius. And the a is going to be this radius. So in fact, that would be mod b would be equal to mod an plus epsilon, and a would be equal to mod an minus epsilon. And if you look in books, when they do this, they would take epsilon to be equal to mod an over 2. But this shows you that I can make that if I took epsilon really small, I can make that, I could squeeze that between two things as close as I want. One less and one bigger. Does that make sense? Okay, that's a picture proof, which are the best kind, I think. So there's an R that makes that happen. There exists an R such that h of z is less than that epsilon in the picture when mod z is bigger than R. And if I multiply through by the z to the n again, I get the estimate. So check. All right, I'm going to use this basic estimate and Liouville's theorem to prove the fundamental theorem of algebra in no time. Fundamental theorem of algebra says that a complex polynomial of degree n bigger than or equal to 1, p of z, of degree n bigger than or equal to 1, has a complex root. Which means and consequently, you can factor polynomials over the complex plane, over the complex numbers. Okay. Well, the proof is going to be snap. Let's suppose I have a complex polynomial that doesn't have a root. P of z does not have a root. which is a 0. Does not have a 0 on C. Then we know the basic calculus facts hold, and that means that 1 over P of Z would be complex differentiable on the whole complex plane. Well, then we get the basic polynomial estimate. Namely, we would have AZ to the n less than or equal to P of Z is less than or equal to B mod Z to the n when mod Z is bigger than or equal to R. Let's make it bigger. Who cares? It doesn't make any difference. I guess I said greater than, didn't I? And the aha is, if that had no roots, then 1 over P of Z would be entire. Okay, and now I'm thinking of a denominator estimate, which I need a greater than or equal to estimate, and this is the greater than or this is P of Z would be greater or equal to the left-hand side, and we would have 1 over P of Z. If that's a greater than or equal to, this would be less than or equal to 1 over A Z to the n when mod Z is bigger than R. And that goes to 0 as mod Z gets big. In fact, let's see. I claim that means that 1 over P is a bounded entire function. It's clearly bounded far out because it's going to 0 to infinity. And that thing would be the biggest it gets at the radius capital R and gets smaller outside. That's assuming R is bigger than 1. It would get smaller and smaller the farther you go out. So why is that a bounded entire function? Yeah.
Because it's continuous inside the long radius R.
Right. It is a continuous function, and inside the disk of radius R, less than or equal to R, which is a compact set, by the way, it'd be a continuous function on a closed and bounded set, which is another word for a compact set, and so it would assume its max. So I claim 1 over P of Z is a bounded entire function. Let's let M equal the max of 1 over P of Z when Z is less than or equal to R. That's a closed and bounded set. So it's compact. And this is a continuous function. Let's see, 1 over P would be, P is continuous and non-vanishing, so 1 over P is continuous and non-vanishing. And of course, the modulus of a continuous function is also continuous. So this would be continuous on the set mod Z less than or equal to R. So it would have a max. And then notice that let's suppose we can assume, we can take R bigger if necessary. We can assume that R is bigger than 1. Then 1 over P of Z would be less than or equal to 1 over A R to the n, no, Z to the n. And that would be less than or equal, that's even bigger than 1 over A R to the n when mod Z is bigger than R. And so that would be a bound. I get a bound outside there. So 1 over P of Z is bounded by what? The max of the m that I just had. That's the inside bound, and the outer bound would be 1 over AR to the n on C. Liouville's now implies that 1 over P is constant. And of course that would imply that P is constant. And why is that out of the question? Yeah, so why couldn't you have a constant polynomial? I can usually make people sit around for several minutes before they think of the reason. A polynomial can't be constant. And if I locked you in a room and asked you why not, eventually you'd come up with probably the simplest reason. Polynomial of degree n bigger than n1 is not constant because its nth derivative is something, not 0. Because its nth derivative, d by dz n p of z at z equals 0 is n factorial an, and that's not 0. So of course it can't be constant. Questions about that? Well, that's a beautiful thing, I think. It proved the fundamental theorem of algebra with very simple lemma, and it just pops right out. Of course, Gauss was thinking of multiple proofs, and there's various elementary proofs. Even Erdős was thinking about multiple proofs of the fundamental theorem that avoid analysis as much as possible. That offends me, though. But this is a beautiful one. You can work a lot harder and maybe avoid some of these ideas, but you can do it for freshman calculus just by, if you look at, if you take 1 over P of z like this and ask where is it maximum, and then you just look at how an analytic function in a circle around a maximum would have to behave, it would have to get bigger than that maximum. And you can do that in a very elementary manner. So I could do this in freshman calculus if I had to. They'd hate me for it, but I could do it. Anyway, this is a beautiful one. As long as I'm doing beautiful things today, another beautiful thing is Morera's theorem. We've done all the work we need to do to prove Morera's theorem. And Morera's theorem shows us the necessity of thinking about integrals around closed contours when we're thinking about analytic functions. So let's suppose f is analytic on an open set omega. I'm not going to assume that, sorry. Is continuous on an open set omega. Then the Morera's theorem says if the integral of f around every closed contour is 0, as in the Cauchy theorem, for every closed gamma in omega, then f is analytic. Okay, sounds like it might be hard, but we've actually done everything we need to do to prove this theorem. In fact, note all I need to know, I don't need to know every gamma, I just need to know triangles. So it's enough to assume integral around Q's for triangles. In omega. And of course, when I'm talking about triangles, I'm talking about a triangle with the boundary and the interior. The closure. That's the topological closure, not the conjugate. Just that would mean that we have what we need from Gurzat's lemma. We proved Gurzat's lemma when f was analytic. But if we assume this, then we have Gurzat's lemma, and then the proof means the Gurzat lemma trick. We have the conclusion of Gurzat's lemma. So let's see, we know the integrals around triangles are 0, and that means, let's see, we have the conclusion of Gurzat's on a disk. On a disk, I might as well restrict attention to a disk about Z0 contained in omega. That disk is convex. So we know, so it's nice that little disk is convex because that's where I did this routine. And we can define an antiderivative, f of z equals integral from the center of that disk to a line going from z0 to z of f dw on that little disk. And now the Gurzat trick, the proof that f prime equals little f on that disk only required the Gurzat's lemma thing. Only required integral around triangles f dw equals 0. So I have an analytic function whose derivative is our little f. And today we know, so we have f prime equal f. Today we know that if f is analytic, then so is its derivative. F is analytic because it has a derivative that's equal to little f. So f is analytic. It's analytic on that little disk. And so that was an arbitrary little disk, so I could do that about any point. So f is analytic on all of omega. That's fantastic. A no-work proof of a pretty interesting thing. And here's one thing I love about Morera's theorem. I told you I was saving some things to prove when I could do it, like floating downstream on my back. A corollary of Morera's theorem is that power series converge to analytic functions inside their radius of convergence. Inside the radius of convergence. And the proof is a snap. Let's let me tell you how it goes. Proof. I'm going to use Moreira. So let's suppose the radius of convergence is r. Let's see, here will be z naught. And this is going to be r. Is going to be the radius of convergence of f. And I'm going to have a closed curve inside here. So here's a closed curve, gamma. Then, so gamma is going to be given by z of t as t goes from a to b. That's a that set is a mod z of t is continuous on a compact interval. So it has a max. Let's call that max little r. And of course that little r is strictly less than capital R. So in the picture here, my little r, here's the max it looks like. And that whole curve would be inside there. Okay, let's write f of z as a power series. That'd be a sum as n goes, let's call it the limit, as n goes to infinity of the sum as n goes from 0 to capital N of a n z minus z naught to the n. Let's call this polynomial p sub n. We know that those tend to, remember that if I shrink the radius a little bit, I get uniform convergence. These are going to tend to f of z uniformly. On the set of z such that mod z is less than or equal to r. Little r. I need to shrink the radius to get uniform convergence. Okay, and that means note, we know that the integrals of polynomials are around a closed contour of 0 because they're the derivatives of something. Because Pn of z equals d by dz of the obvious polynomial that you learn in freshman calculus. And when something's a derivative of something, integrate it, go out on a closed contour, and use a fundamental theorem of calculus, and you get 0. Okay, so let me take the modulus of the integral around f, the integral of f around gamma. I guess the easiest way to do this is to realize I can subtract 0 here in the form integral around p. Okay, that's a big fat 0. And now I realize I can combine those and get the integral of something small, f minus Pn of z dz. And I use the basic estimate for integrals and get that that's less than or equal to the max of f minus Pn when mod z is less than or equal to little r times the length of the gamma. It's a fixed curve, so that's just a number. And by uniform continuity, I can make that max as small as I want. So I could make this make less than epsilon over the length for n bigger than or equal to n naught. By uniform continuity. I meant by uniform convergence. Okay. Well, you would think that works great for power series, but it also works great if I had any old analytic function that converged uniformly. Oh, let's see, I need to say something. I skipped it. Did I say? Uniform limits of continuous functions are continuous. Did I ever say that power series were continuous in the early days? I probably said that. So note, I have the hypothesis of Morera's theorem. Fact, uniform limits of continuous functions. This is a math 341 fact. Uniform limits of continuous functions are continuous. So we have the hypothesis of Morera's. Check. So F is analytic. Inside the whole disk of radius and convergence, capital R. Well, this proof can be made to work whenever something analytic functions converge uniformly, and there's a word for that. So I'll say a sequence of continuous functions f sub n on omega converges uniformly on compact subsets. To a limit f if given epsilon bigger than 0 and a compact K sometimes that's written double subset sign. Then there's an n such that fn of z minus f of z is less than epsilon for all z and k when n is bigger than or equal to capital N. And the fact is, let's see some facts. Well, I just told you the fact about uniform limits of continuous functions is continuous, and now the fact is these limits of analytic functions will also have to be analytic. So we say, right, the Fn, this is what I use for this uniform convergence on compacts, a double arrow sign like that. And today's theorem would be if the Fn's analytic and converge uniformly on compacts to F, then the